In this video, we are going to derive the autocorrelation function for two processes, an autoregressive process of order 2 and an ARMA 1,1. We start with an autoregressive process of order 2, which is given by, in its general form, by yt is constant c plus coefficient of order 1 times the first lag coefficient of order 2 and the second lag and a white noise independent error term epsilon t. In order to derive an autocorrelation function, we start by deriving the unconditional mean of the AR2 process. In these derivations, we assume that the yt process is a stationary process, covariant stationary process. And that allows us in a minute to interchange the expected values of the lagged yt values with the expected value of yt itself. So this is under the assumption of the covariant stationarity of the yt process. And so under the covariant stationarity, if we pull out all the expected values of yt on one side, and remember that the expected value of this error term is 0, we can write down this expected value of yt minus phi1 minus phi2, and that being equal to c. Now, let's denote the unconditional expectation as mu, and so mu is given by an intercept divided by 1 minus the sum of the autoregressive coefficients. This also allows us to rewrite the original formulation here by interchanging the intercept as the unconditional mean mu times 1 minus phi1 minus phi2. And so we can write down that an autoregressive process of order 2 can be equivalently rewritten as follows. This representation is extremely convenient for the derivation of the autocorrelation function. And so we got rid of the intercept and instead used the unconditional expectation mu. This in turn allows us to write down the following. So let's denote as gamma j the jth order autocovariance. So that would be the covariance between the yt and the jth lag. And by definition, that is given by yt minus its unconditional mean and yt minus j minus its unconditional mean. And we just derived the expression for the yt minus its unconditional mean. So we can insert this and obtain the following. So you would have the first autoregressive coefficient, then yt minus 1 minus mu, yt minus j minus mu, the second order autoregressive coefficient times the expected value of yt minus 2 minus mu and yt minus j minus mu. And finally, the expected value of the error term at time t and the lagged y. This is the general expression for the autocovariance. Now we are going to look at the closed form expressions for different j's. So first j being equal to 1, and thus our gamma 1 equals to phi1 times the expected value of yt minus 1 minus mu. I'm looking here, and that term is squared. Then you have your autoregressive coefficient of order 2. Then you have yt minus 2 minus mu, and then yt minus 1 minus mu. Again, this by definition is the autocovariance of order 1 for a covariant stationary process. And then you have also your epsilon t and yt minus 1 minus mu. And here we obtain the following. Phi 1 times gamma 0 plus phi 2 times gamma 1. The shock at time period t has nothing to do with what happened in the past. So epsilon t is an IAD white noise process, which is orthogonal to the yt itself. And now with rearranging the terms, we can write down that gamma 1 would be the phi 1 times gamma 0 divided by 1 minus phi 2. Then what happens if j equals to 2? So the autocovariance of order 2 is given by the phi 1 times the yt minus 1 minus mu. And then again, I'm looking here. So j being equal to 2, you here have yt minus 2 minus mu. Then the second order autoregressive coefficient where yt minus 2 minus mu is twice. And finally, you can ignore the rest because again, the epsilon t and the lagged values of the shock do not talk to each other. And so gamma 2 equals to phi 1 times gamma 1 plus phi 2 times gamma 0. This allows us to write down the autocorrelation function in general. So by definition, you need to standardize the autocovariances by the variance of the process. So your rho j equals to 1 for j being equal to 0. Phi 1 divided by 1 minus phi 2 for j being equal to 1. And then you have a recursive relationship. And in particular, you will have the autoregressive coefficient of order 1 times the lagged rho j minus 1 and phi 2 times the autocorrelation with lag 2. And that defines the autocorrelation function for an autoregressive process, which is covariant stationary of order 2. We now move to analogous derivations, but for another process, ARMA 1.1. So we now will have only one autoregressive component with an MA component. Again, the first step is always deriving the unconditional expectation, and that as this simplifies the derivations of the autocorrelation function significantly. Remember, epsilon t is always a white noise process. Both of those terms would be equal to 0. Again, under covariant stationarity, we could assume that the expected value of yt is the same as the expected value of yt minus 1. And so your unconditional mean is given by c divided by 1 minus phi, and so yt as an ARMA 1.1 process. Again, you can rewrite it as with replacing the intercept with mu minus phi times mu, and rearranging the terms, you put yt minus mu being equal to phi yt minus 1 minus mu plus the MA part. As before, we would then derive the jth order autocovariance between yt and yt minus j. And so we take the expected value of yt minus mu and yt minus j minus mu. And again, we insert the definition of yt minus mu. So you would have then 5 times the yt minus 1 minus mu, and then yt minus j minus mu. And then we would have the expected value of epsilon t and yt minus j minus mu. And we also would have theta. Now watch out, the epsilon t minus 1 here would talk to yt minus 1, for instance, and therefore we do not just set this term to 0. Using this expression, we can finally start, and here we would go step by step. So let's look at the variance. So for j being equal to 0, what is gamma 0 for such a process? So insert j being equal to 0 to our derivations before. So you would have yt minus 1 minus mu, yt minus mu. So that's the autocovariance of order 1. Then you would have the expected value of epsilon t yt minus mu, and theta and term where you have your previous lag yt minus mu. And now we'll go and look at these expressions separately. So the first term, that is phi times gamma 1. Let's now carefully examine what's the expected value of the product of the white noise and yt minus mu. So we keep epsilon t fixed, and we insert the definition of yt minus mu, which we just derived. And then we open up the brackets. Now, the current shock and the previous values of the process, these are orthogonal to each other. Then you have the variance of the white noise process. And because it is not an autocorrelated process, this is a white noise process, the third term is also 0. Now we do the same with the third component of the original expression, and we look at epsilon t minus 1, yt minus mu, and we proceed as before. We would keep the epsilon t minus 1 fixed and look at the yt minus 1 minus mu plus epsilon t and theta epsilon t lagged. Now we open up the brackets, and so we have the expected value of epsilon t minus 1, then you have yt minus 1 minus mu, expected value t minus 1 t, theta, expected value of epsilon t minus 1 squared. This expression is exactly the same as the one we have just seen. So we have phi times sigma squared epsilon. Then you have 0 for the autocovariance of the white noise process. And then you have theta times the variance of the white noise process. Combining all of this together, we derive the expression for the gamma 0. So we would have phi times gamma 1 plus sigma squared of the white noise and theta times phi plus theta sigma squared epsilon. We then go back to the original expression for the jth order autocovariance and consider the first order autocovariance. So for j being equal to 1, our gamma 1 equals to phi times the expected value of yt minus 1 minus mu squared plus expected value of epsilon t yt minus 1 minus mu and theta expected value of epsilon t minus 1 yt minus 1 minus mu. The first term is the definition of the variance of the process. This we have just obtained. The next term would be 0. And the other term, again, we can look up into our previous derivations. And we have seen that that term would be equal to sigma squared epsilon, not forgetting that this is multiplied by theta. And now we can combine two expressions, one for gamma 1, the other one for gamma 0. And in particular, for the gamma 0 expression, let's insert the expression for gamma 1, which is phi times gamma 0 plus theta sigma squared epsilon, and then the sigma squared epsilon, which is multiplied by 1 plus theta phi plus theta squared. Then gamma 0 and 1 minus phi squared can go on the left, and phi theta times sigma squared epsilon can be combined with the rest. And so the gamma 0 would be given by 1 plus 2 times phi theta plus theta squared divided by 1 minus phi squared times the variance of the white noise error term. And in turn, this expression could be multiplied with phi, and you obtain the first order autocovariance. For the j being equal larger than 2, you get your gamma j being equal to phi times gamma j minus 1. And so you can obtain the expression for the rho j, as we did for an autoregressive process of order 2, by dividing the gamma j by the gamma 0. This concludes this video. Thank you very much for your attention.